Good evening and welcome to the Exploratorium and to tonight's presentation of Everything Matters, Tales from the Periodic Table. Tonight, zinc. We are working our way. We just made our way through all the transition elements on that top row there. We'll see that in a moment. I'm Ron Hipschman. I'm your host for Everything Matters tonight. And we're going to, again, like I say, we're going to be exploring zinc. I hope that you all got your collectible card. You could hardly miss it. It's on your seat. So if you don't have it in your hand, you're sitting on it. And if you have been coming to Everything Matters, you probably have a pretty good collection going on. And if you missed a few of our Everything Matters talks out on the in the entryway there, I think we have every card so you can fill in your collection of element cards. By the time we're done with this, you'll have at least 119 of these things, and I will be in my 70s. How many people have been to After Dark before? How many times is your first time at After Dark? Oh, good. Okay, that's good. It's good to know. I hope you're enjoying After Dark, enjoying the inflatable show out there. I just wanted to tell you that if you enjoy After Dark, we have a special membership for After Dark for a very reasonable fee. If you become an After Dark member, you can go to the next 52 After Darks. It's a pretty good deal. So you might want to check that out if you plan to come back to After Dark even a couple of times. It's going to be worth your while. Our program tonight is about an hour long. We break it up into two parts. I'm going to talk really about the chemistry, the history, some of the applications of zinc. And then following me, we have a guest speaker, Janet King, and she's going to talk about her research on zinc in nutrition and metabolism. So it's actually going to be a really interesting talk. I hope you should stick around for all of it. We're going to take a little break in the middle to switch slides out, but don't go away. So I'm going to start off with zinc here tonight. And zinc, let's bring up the periodic table. Everybody's familiar with the periodic, well, most people are familiar with the periodic table. Zinc is found over here. We've actually worked our way all the way across the table. We're at zinc now. Zinc is element number 30. Now that 30 is its atomic number, and that's the number of protons in the nucleus. That uniquely defines the atom. So every time you go up by one proton, you have a brand new kind of atom. So last month with 29 protons, we had copper. Next month with 31 protons, we're going to talk about gallium. Something that you probably haven't seen. Gallium is not one of those elements that most people have held in their hand, but it has some very unique properties. We hope you're going to come back for gallium next month. Again, there's variable numbers of neutrons in the nucleus, but if it has 30 protons, that means it has 30 electrons, and the chemistry is going to be zinc. All chemistry happens in the electrons on the outside of the atom. So, zinc was discovered quite a long time ago. It was named by this guy was Paracelsus, and he may not have actually discovered zinc. It may have actually been discovered in India maybe 400 years before his, but in European history anyway, he discovered it and named it zinc, and that was a German word which stands for prong or tooth. And because zinc, if you purify the actual metal, it has kind of a crystal structure that makes it kind of spiky. And so metallic zinc has that kind of look to it. It's kind of needle-like. And so from the zinc, from that spelling, we get our spelling of zinc, Z-I-N-C. The first guy to actually purify the metal was this fellow, Andreas Marggraf. And he first purified it in 1746. I always have to look at my notes here. I can never remember those dates. But it was probably purified, again, like I say, before that in India, maybe 400 years before that in the 1300s. So again, looking at it from a purely European point of view, these two guys were kind of important in the history of zinc. Alessandro Volta and Luigi Galvani. Galvani was hung frog's legs from an iron hook, but he touched the frog's leg with a piece of copper, and they were connected to each other. The iron and the copper were connected, and the frog's leg jumped. And he thought this was something that had to do with the animal producing electricity, which was not the case, but He was a contemporary of Volta's, and Volta was the fellow who showed that current can flow with nothing living in there. And we'll talk a little bit about that later, what some of the things that Volta did. Zinc is, there's one mineral that's the primary mineral where you get zinc, sphalerite, which is just a zinc sulfide. Sometimes there's some iron mixed in there, but it's mostly zinc, about 60% zinc. And so that's where you refine it from this mineral. It usually occurs along with other sulfides. So you'll find it with galena, which is a lead sulfide, and iron sulfide. So they usually kind of combine. But in sphalerite, most of the metal in there is zinc. And it's found all over the world. Zinc is not one of those things that's found kind of locally in a couple of places. Zinc, as you can see, is found in a lot of places all over the world, and these are the major manufacturers of zinc, or the miners of zinc. So you can see that China and Australia are quite large zinc producers, and even the US and Mexico and a lot of South America. So it's found in a lot of places. It's not one of those things that one country can actually mine and like rare earths, which are found a lot in China, and you can monopolize them. Zinc is found everywhere. So it's very common, fairly common element, at least on the surface of the Earth. It's not really worth very much, about $1.40 a pound. So it's a pretty cheap element as well. But the $1.40 number goes up and down as metal prices do, spot prices go up and down. I just thought it was interesting to see how, if you had actually bought some zinc back in like 2016, you could have tripled your money. But buying zinc means you have it takes a lot of zinc to make any money. You'd have to fill your garage with zinc. So if we look at kind of how rare it is in the universe, zinc is like the 25th most common element. It's not the least common, but it's not the most common either. Hydrogen, of course, is the most common element. It's about 1/1,000,000% of the universe is zinc. So it's not really a lot of zinc in the universe, but it's enough that, especially when you concentrate it into a planet, a rocky planet, it adds up. If you look at the amount in the sun, it's pretty much the same, because the universe and the sun are made out of pretty much the same thing. It's the 23rd most abundant element in the sun, because the sun is not a star that was made at the time of the Big Bang. The sun is made out of the recycled elements from dying stars that have exploded their heavier elements out into space, and the sun is condensed into from those supernova remnants and explosions of white dwarf remnants. And so the sun has a little more zinc than the universe at large. If you look at meteorites, since meteorites, some of them tend to be metallic, it's a little higher. It's like the 20th most abundant element in meteorites. And if you look at the crust of the Earth, well, you're still kind of up there. It's the 23rd most common element in the crust of the Earth. It's more common than some of the elements we've already been through, but less common than some of the other elements in the Earth's crust, silicon and oxygen and iron and things like that. It's not very common in the ocean, however. It's pretty low in the ocean. It's about the 23rd most abundant element in the ocean. It only makes up like 30 parts per billion in the ocean, so it's pretty low. And but in the human body, let's go to the human body. We actually have a lot of zinc in us. We have a lot more. It's the 15th most common element in the human body. So we have a good amount. We concentrate a little bit of zinc in our bodies compared to the crust of the Earth or the sun. Well, and so we're going to learn more about zinc in the body later on. Zinc is made mainly in exploding supernovae and exploding white dwarfs. It has to be made by in a very hot core of a star. Anything past iron, all the elements past iron, pretty much have to be made in some kind of very, very, very hot explosion. Because when you fuse elements into zinc, you lose energy. So a sun can't use fuel to make zinc and then get energy out. It costs energy to make zinc in stars. Now I mentioned that zinc always has 30 protons, but it can have a variable number of neutrons. And when you change the number of neutrons, you make different forms of zinc, and those forms of zinc are called isotopes. iso meaning the same and topes meaning place. So the same place in the periodic table, but lots of different forms of it. These chemically would all react the same. This number that you see here, that's if you add up the total number of protons and neutrons, that's this number up here. So there are 30 different isotopes of zinc. That's a lot of different isotopes of zinc. However, most of them are not stable isotopes. Of all of these 30 isotopes, there's only 5 of them that are stable. 64, 66, 67, 68, and 70. And so these are the ones that make up all of the zinc in the crust of the Earth and the oceans and the sun, because these are the non-radioactive. If we look at the radioactive isotopes and what are the longest lived of the radioisotopes of zinc, well, actually, let's do this first. Actually, the zinc 64 is 49%. So half of all the zinc is this zinc 64, another quarter of it this zinc 66, and pretty much almost the rest of it is zinc 68. So what about those radioactive ones, though? If you look at the radioactive ones, you see that the longest half-life is zinc 65 at 243 days. So basically everything that's not here is less than a minute. So basically all the zinc that's radioactive in the Earth has decayed away. There's no more radioactive zinc in the Earth. And actually, even the stable isotopes, the ones I said were stable, zinc 64 actually has a half-life of 4 times 10 to the 18th years. That's a long time. The universe this is about, and zinc 70 is 1.3 times 10 to the 16th years. Now that's actually pretty long. I mean, zinc 64 has its half-life. Half of it would decay in 312 million times the age of the universe. We've only actually gone one age of the universe so far. And the second isotope would decay in 18 million times the age of the universe. So we call that stable. For all intents and purposes, those are stable. Zinc is a kind of a silvery white metal. Here's a zinc ingot. This is what zinc looks like. So this is a bar of pure zinc. You can come on up and play with it after if you want. Kind of a nice silvery metal. It doesn't rust very readily, at least in the atmosphere, because it actually forms a layer of oxide on the surface, and that keeps the rust from happening further down. The density of zinc is a moderately dense element, 7 grams per cubic centimeter. Anyone remember what the density of water is? 1, right? So it's 7 times the density of water, and you can see here it's about, iron is just a little bit, 7, 8, 9. Iron's a little bit denser than that. And if you want to play a little bit with density, I have some cubes and some samples of, well, mostly elements down on the stage there. Wood, plastic, and actually here's what I have down there if you want to check it out. We have tungsten, which is really dense, and lead, and copper, and iron, and aluminum, and magnesium. Oh, I missed one. There's zinc. So zinc is kind of in the middle of all those. I don't have a cube, unfortunately, of the right size. Here, I'll put this down there so you can sort of compare, although it's not the same size as the cubes. It's a pretty soft element. You can almost dent it with your fingernail, but not quite. Here's kind of a Mohs scale of hardness. And zinc is right there. It's hardness of about 2.5 to 3. So you'll notice that dentin teeth are harder, so you could probably bite zinc and make a mark. I would not recommend that, although maybe Janet can tell us whether you should be biting zinc or not. I don't know. It's pretty soft stuff. Not good for structural. It has electrons flailing around on the outside of it, so it tends to be a somewhat larger atom than hydrogen. We always compare them to hydrogen here. It's about not quite 3 times the size of a hydrogen atom. If you heat it up, put it in a flame, zinc makes a spectrum, and the spectrum of zinc is actually fairly simple. It doesn't have that many bright lines in it. Compared to some of the others like iron, iron is just totally, there's thousands of lines. Zinc is much simpler spectrum. I don't know why, but there it is. And if you actually can see this in the spectrum of the sun, if you looked at the spectrum of the sun, it would look sort of like this. And I've circled 3 of the dark lines that are caused by zinc. Those are pretty much the only visible dark lines that zinc causes in the visible part of the solar spectrum. All these other dark lines are caused by other elements in the outer atmosphere of the sun, absorbing light from the bright white part of the sun, the photosphere. So the 2 lines here from sodium, and there's some dark lines here from magnesium and hydrogen. And hydrogen up here. So these are, you can tell what the sun is made of just by looking at the light coming from the sun. That's actually a pretty cool thing. You don't have to go to the sun and scoop a spoonful of sun up and put it into your spectroscope. You just have to look at the light coming from the sun, which means we could also tell what all the stars are made out of. Very, very powerful technique, spectroscopy. So what are some of the applications of zinc? One of the largest is when you combine it with copper, you get this beautiful golden metal, brass. Brass is about 65% copper and the rest zinc. And it's kind of a nice heavy metal. It's fairly expensive because most of it's copper. Fairly dense metal too. So, and lots of things are made of brass. Of course, instruments are almost all the brass, well, the brass instruments are made of brass, yes. Duh. You know, doorknobs, and this is shells for bullets and artillery are made out of brass as well. Lots of things are made of brass. The penny is an interesting zinc object. We did this, I used this slide last month, so if you were here last month, my apologies, I'm going to reuse this slide. Originally, up till about 1837, pennies were 100% copper. And then from 1837 for 20 years, they added a little bit of tin and zinc. So it became kind of a bronzy brass. Bronze is copper and tin, and brass is copper and zinc. So it's kind of a copper zinc, a bronzy brass for a couple of years there. Then it went to a cupro-nickel kind of mixture, and then up to 1962 it was 95% copper, and it went back to this kind of bronze brass kind of thing. Of course, during the war, they needed the copper for the shells, and so during the war in 1943 there were just steel pennies. But after the war, up till 1982, it was still 95% copper and 5% zinc. Not quite brass, but brassy, I guess. But now, from 1982 to now, pennies are only 2.5% copper and mostly zinc, which is why I bring up pennies again, which means you can do some interesting things with pennies. One thing you can do is if you take a penny and you scratch it along the edge of the penny, and then put the penny into hydrochloric acid, you get the acid eats the zinc but not the copper, and you get a penny that's empty. This is just a whisper of a penny left. I mean, if I drop it, oops, did you see it flutter? Yeah, if you want, you might want to come up and actually try to. This is just 2.5%. It's just barely a penny. As a matter of fact, if you could manage to somehow remove the copper from a penny, you'd have a zinc penny, pretty much the same as what you see here. It would look something like this. This was Theodore Gray, who has this wonderful site on the internet, periodictable.com, highly recommended. Also, by the way, this is his book, The Elements. I'm going to get over here in the light so the camera can see it. Highly recommended. I love this book. For sale in the store, too. Had to mention that. I love this book. He also did a book on molecules and a book on reactions. But he's awesome. He made a periodic table. It's a table in the shape of a periodic table. And the elements, if you lift them up, have little samples underneath. It's really cool. He's kind of an element nut like me. Really, really good guy. So the penny, as you can see, is mostly zinc nowadays. It's very, very little copper. If you sand a penny, which I did here, I sanded a penny, you can see that it's for the most part, it's a zinc penny. It's probably still worth more than a penny. But if you go back and look, if you have a jar of pennies, save the pennies that are 1982 or before, because they're probably worth like 3 cents. So you could probably sell them for like 3 cents because they're mostly copper. You can barely see the edge of the copper here, just whisper thin. If you take a penny, hold it in a pliers, this is an experiment you can do at home. Get out your torch, hold it in a needle nose pliers, and then torch it. You will melt, the zinc will melt before the copper, and you'll end up with a little very thin copper bag. You have to almost come up and see this. I don't think that the camera up there will be able to see this. Let's see. Can we go to the camera here? I surprised them. They didn't know they were gonna, there we go. I don't know if you can see, it's a little, yeah, you see it's kind of bulging at the bottom? You get a little copper bag of zinc at the bottom, with zinc at the bottom. Kind of cool. Good catch. It looks kind of like that. I was kind of surprised when I do that. Melting it, you can, if you put a hole in the bottom, the zinc will just drip out. If you dip steel into zinc, the steel will get coated with zinc, and if it cools slowly enough, you can see zinc crystals on the surface of the steel. They look like this, and you've probably seen galvanized metal. I have some pieces right here. These are galvanized pieces of steel. Maybe we can see that. Well, I have a slide. You don't have to bring up the camera. I can pass them around, actually. Here, we'll put one here, put one here. You can take a look at that. You can see the crystals in the galvanizing. It depends on how slow the crystals freeze. This piece here, it's hard to see the crystals because this one cooled off really quick. So you got really small crystals. But those are a little bit bigger. And these things, it's called galvanized steel. You know who that's named after? Galvani. Yep, Galvani. So here, Galvani reappears here. And galvanizing is a way to keep steel from rusting. The zinc protects the steel. Again, it forms a layer of oxide on top of the, just a thin layer of oxide on the top of the zinc, and then it stops. It's called passivation. You can also keep things from rusting by dipping them in zinc. This tiny nail that I have here was just dipped in zinc. So these are galvanized as well. Knew that was going to happen. Oh, my voltaic pile just got destroyed. That's all right. I can build it for you in front of you. Okay. You can build yourself. We'll get to a voltaic pile rather. That actually gives me an opportunity to do that. Okay. Galvanized steel. Again, you can dip bolts, and most bolts and nuts and bolts that you see in our shop are dipped in zinc, and that makes them less rustable, although we can't use these here outside because the salt water will actually eat through even the zinc. If you have a boat, or in our case, our buoy that's in the lagoon, and you want the seawater to eat some of the metal but not other parts of the metal, you can strap zinc plates to that, like in our case, on our buoy out in the lagoon there. It's not really a lagoon, but out in the, between the two piers there. And when the seawater attacks it, it will attack the zinc, not the steel of the buoy. And so you can also attach them to ships. So these are called sacrificial anodes. It's actually an electrical thing going on there. So the zinc slowly is eaten away, and you have to replace it we replace ours every year. Zinc is in the form of zinc sulfide. So zinc and one zinc atom and one sulfur atom is the basis for all glow-in-the-dark material. So like this powder right here I have is a zinc sulfide, which is it has another element, impurity, that lets it glow. Can we turn the lights down? Let's see what happens when we turn the lights down here. Oh, lights go down. We should have practiced this ahead of time, huh? There we go. Okay, so I have an ultraviolet light here, and if I charge it up, you can see that this is this glows in the dark, and this is zinc sulfide powder. This powder is put into, if you dissolve it into oil or a water-based paint, makes glow-in-the-dark paint. You could also put it into pieces of vinyl. How many of you have been in our shadow box? The shadow box. This is the basis for our shadow box, where you stand against the wall, and there's a photographic flash that flashes the wall, and you move away, and your shadow, it gets stuck. It's very Peter Pan-ish. Shadow, you can separate yourself from your shadow. Our box doesn't actually we used to use this phosphorescent vinyl, but now we use, and you'll like this, we use phosphorescent formica. So laminate. You can actually go out and buy phosphorescent laminate. So if you are redoing your kitchen at any time in the near future, I know that laminate is kind of tacky now, but maybe it's coming back. You could go out and buy sheets, 4x8 sheets of glow-in-the-dark laminate. Think of your kitchen cabinets and your tables and counters all done in glow-in-the-dark. You go out at night to get your little snack. Don't have to turn on the lights. It's pretty cool. Okay. Now, when you put zinc in contact with copper, this guy here discovered that you can actually create, well, a voltage. It wasn't called voltage back then because he was, Volta gave his name to that, but he was able to make electricity, and he did that with a pile of zinc and copper disks, which I, of course, just dumped on the floor. So maybe I can recreate it here quickly enough. Let's see. I have my salt water, and we can re-soak our little cardboard disks here. And what I need to do is let's look at the structure of a voltaic pile. We start off with, I started from the top there. So I have a zinc. Zinc is just, again, I'm just using washers from our shop because they're plated with zinc. So it's a good source of zinc. And the copper, I'm just using pennies. And I know you're saying that pennies have zinc on the inside, but if it's copper all the way around on the outside, it's copper. We don't worry about the zinc on the inside. The inside doesn't matter. So all I have to do here is take a disc of, salty cardboard, saltwater cardboard, and then I can put a penny on top of that, and I put a washer, and then a salty piece of cardboard, and then a copper and a washer. I just have to do this a few times, and another piece of cardboard, and another copper and zinc, and let's just do it a couple more times. A piece of copper. I need to get enough voltage, and copper, and one more time. Okay, and one more piece of cardboard and a piece of copper. Oh, actually, I have this copper. I have this penny that I've soldered a lead onto. Now one of the clip leads is connected to the bottom of the pile, and the other clip lead is going to be connected to the top of the pile, and I've connected both leads to an LED. Let's see what we can see. And I press this on top. What do you see? You don't see anything. That's what I get for, I may have switched the clip leads here. Let's switch the clip leads because the diode only works one way. Okay, this worked ahead of time. There we go. Can you turn the lights down a little bit here? Maybe I can put it here so you can see. Can you see the LED lit there? Maybe not. It's lit. It's just hard to see.
How much current?
only a couple milliamps here. So it's very weak. I really would have to build a few of these piles and put them together. So it was glowing there, now it's no longer glowing. But you can make electricity. The basis of a battery, as a matter of fact, if we look at batteries, let's go back to my slides. This is the basis of all these kind of batteries, and inside of those batteries, there is, you see the green here is zinc. It's a zinc can, and inside the zinc can is essentially a spacer and a paste, which is sort of like what my little cardboard discs were doing there, and a carbon rod. Instead of using copper, they use carbon, and this is what's inside of a carbon zinc battery, which is kind of the normal everyday cells that we use in our C cells and D cells and A cells. That kind of battery. It's not the only kind of battery there is that uses zinc. There's another kind of battery called the zinc air battery, and this is almost like a fuel cell. It actually uses oxidation of zinc to produce electricity, and these are beginning to take the place of kind of the more toxic mercury batteries. So I just want to talk about one chemical. I do have a chemical here of zinc that's kind of important that you've seen before. This is zinc oxide. It's just a beautiful white, super white powder, and it's used in a lot of things. It's used in, well, this diaper rash Desitin, right? This is this is 40% zinc oxide, so it's 40% this powder, and the rest of it is like petroleum jelly and a couple of other ingredients. But the main ingredient is in there is zinc oxide. My favorite product is not Desitin. My favorite product of the zinc oxides is actually this one here, Bordeaux's butt paste. But I love a company that's willing to take a risk on naming their product. Also, another interesting product, well, a product that has zinc oxide is Caladryl or calamine lotion. Calamine is actually mainly zinc oxide, and it has, the reason it's pink is that it has just a little tiny bit of iron oxide, rust, inside of it, about 0.5%, and that's what kind of colors it red. I don't know what the function of the iron oxide is, but the main part of it is just zinc oxide. Zinc oxide is another interesting substance. I just want to do a quick experiment before we leave it. I want to open this bag here, and I want to put a spoonful of this on this plate here. Zinc oxide has a really interesting property. It is called thermochromic. We can go to the camera that looks at this, so hopefully you'll be able to see this on the camera. Thermochromic things change color when they change temperature. That's what I have the torch here for. Andrew, I need to have someone on the fire extinguisher just in case I set myself on fire. I'm not allowed to do the fire extinguisher and the fire. Kind of makes sense, I guess. Because if I set, Andrew, by the way, is in our public programs, and if without him, this thing doesn't happen. He's responsible for this place. Yeah. He never gets acknowledged. Yeah, about time. So I'm just going to flame this thing and watch what happens to the color of the zinc oxide. It's going to change color because it's hot. Can you see what color it's turning? Oh, of course, pretty obvious. Turns a beautiful yellow, and then when it cools down, it goes back to white again, thermochromic. So I could do this as many times as I want. Now that I've applied a little more heat, it's going to take a little more time to go back to white. But that's kind of cool, don't you think? Thermochromic. Remember those t-shirts that change color when they got warm? Same idea. Chemicals that change color when they're warm. Okay, someone just sent me, like right before this talk, a picture of a car that he used to, was in charge of keeping an eye on during the summer. It's a Lamborghini, but it's not just a Lamborghini. This Lamborghini was originally purchased by the International Lead Zinc Research Organization. Yes, believe it or not. And they wanted to say, how much of this can we turn into zinc? So they took virtually the entire car, they remachined into zinc. So it's not drivable, of course, but it's a beautiful car, but it's made out of zinc, and I thought that was kind of cool. I am not going to talk about the biological uses of zinc, because our second speaker is going to do that. I'm just going to leave you with an elemental haiku for zinc, which comes from Science magazine. Clasp your neighbor tight, sound the music while you dance, trumpet, bugle, horn.